The next video lesson will look at Practice Test B Objective 4. We are being asked to calculate the enthalpy changes that occur using a warming or cooling curve, including phase changes such as melting, freezing, boiling, or condensing. Our first question begins by saying, how much heat in kilojoules is released when 150 grams of steam, called gaseous water, at 155 degrees Celsius is converted to ice at negative 20 degrees Celsius. The rest of this question is giving us information about constants we would need for each line or line segment on our phase diagram. Let's begin this problem by getting an idea of how many line segments we have to solve for. We will need to draw an XY axis on our paper, labeling the y-axis as temperature in degrees Celsius. Heat content goes on the x-axis, and that's measured in joules of energy. We are beginning this problem up high at a hot temperature of positive 155 degrees Celsius. We are going all the way down to very cold, negative 20 degrees Celsius. Between those 2 points, we have phase changes for water. We will also need to record that at 100 degrees, we know that the gaseous steam will liquefy. That process is known as condensation. There is another phase change that occurs at 0 degrees when the liquid water freezes to solid ice. There's a total of 4 temperatures we'll need to keep track of. In our first line segment, we will be looking at beginning with point A, moving to what I'll call a point B, where we take the steam or gaseous water and begin cooling it from 155 to 100 degrees. Line segment AB represents steam as it's cooling down to 100. Then we notice that there's a flat line on our graph. From point B to point C, we are taking 100% of the gas molecules at point B and we're liquefying, which is called condensation, from moving from a gas to a liquid. This value, as we calculate, is known as the delta H of vaporization. At point C, 100% of the molecules have now reached the liquid phase. You'll notice a drop in the temperature. From point C to point D, we are now cooling the liquid phase. At point D, we notice another flat line. Moving from D to E takes the liquid, and by point E, they've 100% converted to solid ice. This is known as the delta H of fusion, taking the liquid and causing it to turn to solid ice. We have one more line segment from point E to point F, in which we're taking that ice at 0 and cooling it further to negative 20. In this particular problem, I'm counting 5 line segments. We will begin by taking a look at line segment AB, doing a calculation for steam as it's cooling. We'll then calculate for line segment BC, knowing that that's the delta H of vaporization. That's a phase change. We will then calculate for line segment CD, in which the liquid is cooling. Line segment DE is the phase change, delta H of fusion. And the final line segment EF, is when the ice is cooling even further from 0 to 20 degrees negative. Each one of these line segments will have its own calculation. I notice that the amount of water we're calculating for is 150 grams of water. And I know that when I MC delta T, that's when I have slopes on the line. When I MC delta T, I need to use mass of water. But when I'm phase changing, where there is no slope but a phase change occurring, we need to calculate using mole numbers. I like to have both of those numbers handy so I can place into the formula the correct value matching unit. I'll use the molar mass of water, which is 18, to convert my 150 grams. Divide by that 18, and that gives me a value of 8.33 moles of water. Considering at some points we need the mass, I like to have the 150 gram ready, but at some points we need the word mole, so we'll have that value ready as well. We will begin then calculating MC delta T for line segment AB. Getting our parentheses ready, M times the specific heat times the change in temperature. I'll divide by 1,000 so I can get my answer from joule into a kilojoule directly. The mass we said was 150 grams. Our specific heat for steam, looking at your test taking tool page, that value is 1.84 joule per gram degree Celsius. The delta T is taking me from 155 down to the point B, 100. It has changed by 55 degrees Celsius. I will hit 150, the mass of the water, times 1.84, the specific heat of gaseous water we call steam, times the delta T, 55, and I will divide that by 1,000 to change my joule into a kilojoule, knowing that we'll need to add like units. This gives me a value of 15.18 kJs. In the next line segment, we move from point B to point C, called the heat of vaporization. With this line segment, we begin with our constant, the heat of vaporization of water, 40.7 kJs per mole. It takes 40.7 kilojoules of energy for every 1 mole of water. The number of moles we are using we calculated earlier, 8.33 moles, and you can just set that over a 1 so you can see how the moles have canceled. We'll calculate that and already be in a kilojoule of energy. 40.7 times 8.33, my calculator reads 339.03 kilojoules of heat. In our next line segment, we have a slope of the line from point C to point D. We have a temperature changing. It's an MC delta T problem, where this time we're in the liquid phase. We are using again the same amount over and over, 150 grams of water, but now we match the specific heat constant to the liquid value, 4.184 joules per gram degree Celsius. To move from point C to point D, we started at 100, went down to 0 degrees. It changed by 100 degrees Celsius. Let's divide that answer by 1,000 to change our joules into kilojoules of heat energy, knowing that we'll have to add like units. Let's hit the mass, 150, times our specific heat constant for liquid water, 4.184, times our temperature change of 100, and divide by 1,000 to change our joule into kilojoules, and I find 62.76 kilojoules of energy for line segment CD. What we'll need to do next is the phase change from point D to point E. Our constant we know for the heat of fusion, 6.01 kilojoules of energy for every 1 mole of water. But we are using 8.33 moles. And we may certainly set that over a 1 to notice how the mole units have canceled. 6.01 times our number of 8.33 gives us a value in a kilojoule of 50.06. One more line segment is the final temperature change. We have an MC delta T problem for ice. We are having 150 grams stand for the M, the mass of our problem. Specific heat constant unique to that of ice, 2.09 joules per gram degree Celsius. The final temperature change to move from point E to point F went from 0 to negative 20. 0 to negative 20 is a change of 20 degrees Celsius. We'll divide that by 1,000 to get our answer into a kilojoule, knowing that we'll have to add like units. 150, the mass of our water, times 2.09 specific heat of ice times the delta T of 20, divide by 1,000 to convert joules to kilojoules, and I get 6.27 kJs. The last thing we'll need to do is add those values together to report a final kilojoule. We'll take 15.18 and add 339.03 plus 62.76 plus 50.06 plus 6.27. My final answer, 473 kilojoules of heat. There's a very important word up here that talks about releasing heat. The process starting hot and cooling down, as in this phase diagram, represents an exothermic process. Every one of our values is an exothermic process. My final answer should be reported with negative sign to show that we know it's exothermic. Negative 473.3 kilojoules of heat is our final answer for problem 1.